Hi, my goal here today is pretty simple. I'm going to try to introduce you to rotational motion, and specifically we're going to talk about rotational kinematics. This is much like linear kinematics, only with things that go in circles, or not even circles, but part of circles and basically not in straight lines. So our linear kinematic variables were x, v, and a, and what we're going to do is we're going to try to relate those to angular type of motion. So I've already drawn on here something that vaguely resembles a circle. These are supposed to be radii, and the little blue things here are thetas, indicating the angle. So that's our first thing, which is that the angle, the angle is represented with theta, and that's measured in radians. So we have angular position is given by theta. So for instance, I could label this as 0 radians right here if I wanted to, and then this would be some other angle here and so on. And by the time that I get down to, say, right around here, we would be at a position of pi over 2 radians. So that's how we would measure the rotational distance or angular distance. If it goes around one full circle, that's 2 pi. If it goes around 2 full circles, that would be 4 pi, and so on. So we just keep stacking up. It's an additive effect. If we go the other way, then we would have negative radians. So one question that could arise is, first of all, why do this? Why describe motion in terms of angles? One reason why it can be useful is because of differences in how things work depending on where they are on a circle. So for instance, if this is, imagine that this is just a point going around the edge of a circle, of a wheel for instance. This point travels from, let's go with yellow, from here to there, right? So I have a delta x. In this case, it traveled from there to there. On the other hand, if I go much further in, and we go from here to there, that's a very different delta x, right? So I have delta x1 and delta x2. What's interesting, though, is that if we go from these locations to their new location along this line, both of these have traveled through the same angular distance. And what that means is that rather than having to describe every point on this circle, or every point on this disk, as moving a different amount, which is what would happen if we dealt with linear motion, we can describe all of them as moving through the same angular distance. And if we think about these things as vectors, it gets even more important to treat things as angular, because if you have a point that's over here, and it moves part way along the circle, right? If that's a vector, it could be the same delta x1 that I had over there in terms of its magnitude, but its direction is totally different. This one was moving mostly down, and this one's moving mostly to the left. In terms of the angular displacement, though, they all move through the exact same angle, including direction. And you might be wondering, well, how is this possible? It looks like it's moving through a different angle, right? If we go from there to there, that looks like a different angle than this one, and you're wrong. The reason for this is because we define the direction of angular motion as, well, into or out of the screen in this case. So you could think of it as sort of like clockwise or counterclockwise. I'm going to get more into that and how we determine that a little bit later. But in this particular case, we would describe the delta theta as being directed into the screen. Okay, so this is how we would describe it. If it was moving instead counterclockwise in this case, it would be coming out of the screen. The reason why this is the case is because if we're trying to define this as a single uniform motion, we can't describe it as moving left or right or up or down, because it's clearly not doing that at all different points in time. We also want to be careful about clockwise and counterclockwise. If you can imagine that I'm spinning this around, to you looking at the screen, it looks like it's moving clockwise. But if you could imagine that this is an actual physical wheel, and you stand on the other side of the wheel and watch it, to you it won't be going clockwise, it would be going counterclockwise. So we don't want to use clocks, generally speaking, as our way of describing how things go. We want to use something that everybody will agree on. And like I said, I'll talk to you about this more in class. Now, one question that might arise is, how do we actually convert these linear distances or linear displacements to angular displacements? And that's why I have this little conversion column. By the way, when you look at this table here, we're eventually going to make it about 10 There's going to be like 10 different terms that we're going to put in there. So make sure you leave enough space, that way you'll have a nicely well organized layout there. So how do we convert? Well, this is actually something that you should be familiar with. If you've studied math up through trigonometry, then you should know that an angle, theta, is defined by the arc length, which is normally denoted s, divided by the radius. Now for us, this is synonymous with delta x over r. So we have theta, I'll write it like this, d theta equals delta x over r. This is the definition of a radian. So 1 radian is when the arc length is equal to the radius. If you didn't know that, then you need to do a little bit more work maybe in this unit to get familiar with how this works out. So one thing that we can do then is we can say, for instance, that delta x equals delta theta times r. And so for any given constant delta theta, which we see here for instance, the further out the point that we're interested in is in that circle. So the bigger r is, the bigger the distance, the linear distance that we've actually traveled. So here's our conversion. I'm just going to forego the deltas here. Theta times r. Now another thing that might make you wonder here a little bit is that this is in meters, right? So we have meters. Get this cursor over there. So we have meters, and that's going to be equal to radians times, and then the radius is also measured in meters. And so you might be looking at this and saying, I thought the units had to be the same. And they do. It turns out that radians are not a unit. We use them as a placeholder. How can I say that they're not a unit? Because if I go back to what a definition of radian is, it's the arc length, which is in meters, divided by the radius, which is in meters. And if you have meters over meters, you get unitless. I'll follow it down here. Unitless. There are no units. However, we feel bad about this. We think that radians or angles work very hard, and so we don't want them to go around without any sort of a unit. It's also awkward sometimes if you don't assign things units, so we just make up this unit called radians, and then as soon as something better comes along, like a meter, we just completely ignore the fact that the radians were ever there. So that's the basic idea. So we have meters equals radians times meters, which ends up just being equal to meters. So that's our basics with position. We have linear position, angular position, linear displacement, angular displacement, and this is the way that we can convert between them. If you have a stick and you spin it around in a circle, every part of the stick, assuming that it's a rigid body, which is something that we're going to assume for this unit, this will be constant for every part of the stick. And so the parts of the stick that are furthest from the axis of rotation, which in this case is right here, will be going the furthest distance. What we're going to do in the next video is take a look at some of these other parameters like velocity and acceleration. Acceleration is particularly tricky, so be prepared for that.